Life on K2-18b has already been found. That is the claim people wanted to believe when the new data hit. But the closer you look, the less stable that sentence becomes. So what does the data actually confirm, and what still refuses to be settled? At first, this looks like one more distant planet story. Then the numbers start to stack up, the chemistry starts to clash, and the easy answer starts to fall apart. By the time we reach the end, the question is not only whether life is there, but whether we are even looking at the planet the right way. If you want to be part of the crowd that waits for the full picture instead of the fast headline, stay with this from the start. Subscribe now and keep close, because this story is still moving. K2-18b did not become important because anyone saw forests, oceans, or cities. It became important because of a much smaller clue. A star dimmed, very slightly, on a repeating schedule, and that tiny change told astronomers that a planet was crossing in front of it. That is how this whole trail began. The host star is called K2-18. It is a red dwarf, which means it is smaller and cooler than our Sun. The planet circles this star once every 32.9 days. That sounds fast, but because the star is dim, that orbit still places the planet inside what scientists call the habitable zone. The habitable zone is often misunderstood. It does not mean a planet is friendly. It only means that under the right conditions, liquid water could exist. The right distance from a star is just one piece, and sometimes it is not even the hardest piece. K2-18b is also not an Earth twin. NASA lists it at about 8.92 times Earth's mass and about 2.6 times Earth's radius. That makes it much bigger than Earth, yet still much smaller than the ice giants in our own solar system. It sits in a middle class called sub-Neptunes, and that class is one of the strangest in modern planet science. Why strange? Because we do not have a true sub-Neptune here at home. That means astronomers cannot point to a nearby example and say, "This is how these worlds work." They are trying to understand one of the most common kinds of planets in the galaxy while standing in a solar system that does not really contain one. That alone makes every useful observation valuable. K2-18b is about 120 to 124 light-years away, close enough for major telescopes to study, but still unimaginably far. No probe is going there. No sample is coming back. Everything we think we know comes from light, and light can tell the truth in pieces while still hiding the full picture. That is the rule we have to keep in mind the whole time. The first major step came before James Webb. In 2019, work using Hubble data reported signs of water vapor in the planet's atmosphere. That was exciting for an obvious reason. Water matters to life on Earth, so any hint of water on a habitable zone world gets attention fast. But even then, the situation was more limited than it sounded. Water vapor in an atmosphere is not the same as a living ocean. It does not prove a surface, beaches, rain, or anything gentle at all. It simply means a water-related signal appeared in the air above the planet, if the reading was being understood correctly. So at that stage, the picture was suggestive but thin. There was a planet in the habitable zone of a red dwarf, there were hints of water in its atmosphere, and there was a growing sense that this world might be one of the best places to test whether we can study habitability from very far away. Then the James Webb Space Telescope entered the story. Webb can see parts of infrared light with power and detail that older space telescopes could not match. That matters because different gases block different parts of a star's light as that light passes through a planet's atmosphere. If the pattern is clean enough, scientists can work backward and infer what gases are likely present. This method is called transmission spectroscopy. The name sounds technical, but the idea is simple. A planet crosses its star, a thin ring of starlight slips through the planet's air, and that air leaves chemical fingerprints in the light. The telescope catches those fingerprints and scientists try to read them. There was another reason this planet rose so quickly to the top of watch lists. K2-18b passes in front of its star from our point of view. That alignment is rare and useful. Without it, a telescope like Webb would have a much harder time testing the planet's atmosphere at all. Every time the planet crosses the star, astronomers get one more chance to read the light. But each chance is brief. If the instrument misses part of the transit, or if the star behaves in an unexpected way, the lost information cannot simply be guessed back later. That is one reason every new transit matters so much. Red dwarf stars also complicate habitability in their own way. They live for a very long time, which sounds good at first, but many red dwarfs are active, especially compared with the Sun. They can blast nearby planets with energetic radiation, and over long stretches of time, that radiation can change or strip atmospheres. So even if a planet sits in the right temperature zone, that does not mean its environment has stayed calm. A world close to a red dwarf may face harsh space weather. That can alter chemistry in the upper atmosphere and make life harder, especially if the planet has little protection. K2-18b may be large enough to hold on to its air, but that does not solve every problem. Read is the key word there. They are not seeing clouds drift across the world. They are not landing machines on the surface. They are reading tiny shifts in light and trying to separate real signals from noise, hidden overlaps, and mistaken assumptions. That means every conclusion has to survive a lot of pressure. In 2023, Webb provided the first truly major turn in the story. A team led by Niku Madhusudan at the University of Cambridge reported clear signs of methane and carbon dioxide in the atmosphere of K2-18b. They also found a lack of ammonia. That mix did not fit every simple model people had for the planet. Methane and carbon dioxide matter because they are carbon-bearing molecules. Carbon is basic to life on Earth, but here the point was not life yet. The point was environment. In a hydrogen-rich atmosphere, a pattern with methane and carbon dioxide and very little ammonia can fit the idea of an ocean under the air. This is why scientists became so interested in the exact gas pattern Webb reported. Methane and carbon dioxide together tell a richer story than water vapor alone. They suggest carbon chemistry is active in the atmosphere. That matters because carbon-based compounds are basic building blocks for many of the processes linked to life. But the missing ammonia was part of the intrigue too. If ammonia had appeared strongly, some simpler gas-rich planet models would have looked more comfortable. Its weakness pushed some researchers toward the idea that ammonia might be getting removed, perhaps by dissolving into liquid water below. That is one of the reasons the ocean interpretation gained force. Notice the wording there, might be. That phrase appears again and again because every attractive explanation still leans on model choices. A weak or missing ammonia signal can fit an ocean story, but it can also reflect chemistry we do not yet understand well enough in a hydrogen-rich atmosphere under alien conditions. That is part of what makes K2-18b so frustrating in the best possible way. Each clue seems to point somewhere, but each clue also arrives with a warning attached. Even when the gas detections themselves are strong, their meaning depends on a chain of reasoning. Break one link in that chain, and the picture shifts. That possible class of world has a name. Hycean. The word combines hydrogen and ocean. A Hycean planet is imagined as a world with a hydrogen-rich atmosphere and a global ocean below. Some versions of that picture could, in theory, allow life in the water. Now, the first real caution has to be placed on the table. Webb did not directly confirm an ocean. It did not show waves. It did not show liquid water at the surface. What it showed was a gas pattern that some models say is consistent with an ocean world better than with certain other planet types. That is still important. Sub-Neptunes are very common, and if some of them can host oceans, the search for life suddenly grows wider. But the jump from atmosphere pattern to living world is huge. The 2023 result was a strong lead, not a finished answer. That difference matters more with every step that follows. Then came the clue that changed the tone from important to explosive. Alongside the stronger methane and carbon dioxide result, the 2023 study reported a possible sign of dimethyl sulfide, usually shortened to DMS. That name does not mean much to most people, but in this story it became the center of the storm. DMS is interesting because on Earth it is strongly linked to life. In our oceans, tiny living organisms help produce it. So if you hear that a distant world may have DMS in its air, the human mind races ahead. Maybe something is alive there, making the same kind of gas. But that is where careful thinking has to take control. A gas can be linked to life on Earth and still fail as proof somewhere else. For a molecule to act as a strong biosignature, scientists have to show not only that it is present, but that non-living chemistry could not make the same signal under those planetary conditions. That second part is brutal. At the time, even the research team was cautious. They described the DMS finding as tentative. In plain language, that means it was a hint, not a stable detection. They wanted more data, more tests, and more ways to check whether another explanation might fit just as well or better. The DMS excitement is a perfect example of that problem. On Earth, DMS is strongly tied to ocean biology. Tiny drifting organisms help make it, and winds carry some of it into the air. That is why the molecule feels so emotionally powerful in this story. It seems to whisper life in a language we already know. But Earth-based meaning can become a trap. When scientists talk about biosignatures, they are really talking about context-sensitive clues. Oxygen, methane, sulfur gases, and other molecules do not speak for themselves. They only become convincing when the whole environment around them makes non-living explanations look weak. That is, the standard K2-18b has not yet reached. The parts per million estimate from the 2025 work made that tension even sharper. More than 10 parts per million sounds tiny, and in one sense it is. It means just a few molecules out of every million. But for a gas linked on Earth to life, that amount would still be striking, especially in a distant atmosphere being studied from so far away. Yet abundance cuts both ways. If a gas seems present in an amount much higher than on Earth, that can sound like stronger evidence for life. But it can also mean we are dealing with chemistry and physics unlike Earth's in ways that make Earth comparisons less useful. Sometimes a shocking number is not a clue toward life. Sometimes it is a warning that the planet is stranger than our first analogy. Still, public excitement surged. A planet in the habitable zone, possible water-related clues, methane and carbon dioxide confirmed, and now a molecule tied on Earth to marine life. It was almost too perfect for people not to push the story further than the data allowed. Before we get to the next big turn, make your call now. At this point in the story, do you think the new observations are going to strengthen the life idea or start cutting it down? Drop your prediction in the comments before we go further. The next turn arrived in April 2025. Again led by Madhusudan and colleagues, a new study used Webb's mid-infrared instrument and reported what Cambridge described as the strongest hints yet of possible biological activity outside the solar system. This time, the suggested signal involved DMS and/or dimethyl disulfide, known as DMDS, a related molecule. That claim sounded even louder because of the reported abundance. The team estimated that these sulfur-bearing gases might be present at more than 10 parts per million. That is a tiny fraction in absolute terms, but compared with Earth's atmosphere, it would be extremely high. In simple words, if the reading was right, the amount looked hard to ignore. But now we hit the number that shaped the whole argument. The reported significance was about 3 sigma. Sigma is just a way to describe how likely it is that a signal is real instead of random noise. 3 sigma is interesting and worth taking seriously, but it is not the finish line. For strong claims, scientists usually want 5 sigma. That standard is not magical, but it is much tougher. It means the chance of the result being a fluke becomes very small. K2-18b did not reach that level for DMS or DMDS, so even at the high point of the excitement, the signal remained below the strongest standard. The same double meaning applies to the Hisian idea. People often hear the word ocean and imagine something gentle, blue, and alive. But a global ocean under a hydrogen-rich sky could still be dark, deep, hot, chemically aggressive, or buried under conditions that would crush familiar life. An ocean is not the same thing as a biosphere. And there is another uncertainty hidden inside the planet's size. A world with 2.6 times Earth's radius may carry a much thicker atmosphere than Earth does. If that gas layer is deep enough, then the pressures lower down may become enormous. Any liquid water that exists might sit under conditions far outside the range we normally picture when we say habitable. That matters because temperature alone does not decide whether life can function. Pressure, chemistry, energy flow, and long-term stability matter too. A planet can have water somewhere and still fail every test that matters for biology. This is why scientists now try hard not to use the habitable label loosely. For K2-18b, that label is less a conclusion than an invitation to ask harder questions. The debate over statistics also deserves a close look. To many people, 3 sigma sounds nearly final. After all, it suggests the signal is not likely to be random. But astronomy has learned, sometimes painfully, that complex data can create false confidence when models are flexible and signals are faint. That is why 5 sigma became such an important target, at least today. The Cambridge team said that themselves. They did not say life had been discovered. They said the signal was promising, that the work needed more follow-up, and that an unknown non-biological process could still be responsible. That careful language mattered, even if many headlines did not keep pace with it. Then the doubts started coming in from across the field. Some astronomers argued that the model used to interpret the spectrum was not testing enough alternative molecules. Others said the data might be too noisy to separate DMS or DMDS cleanly from other possibilities. And some questioned the deeper assumption that K2-18b is even the kind of world where a surface ocean makes sense. That last point is crucial. A biosignature does not float free from the planet around it. Its meaning depends on the world. If K2-18b is a thick, gas-draped planet with crushing conditions below, then the same molecule would mean something very different than it would on a temperate ocean world. The nature of the planet and the nature of the gas cannot be split apart. This is where the story stopped being only about one chemical clue. It became a much larger argument over planetary identity. Is K2-18b really a Hycean world with water under hydrogen-rich air? Is it instead closer to a mini Neptune with deep gas, high pressure, and conditions too extreme for life as we know it? Those two pictures lead to very different verdicts. The size of the planet keeps pushing this issue back to the surface. At nearly 9 Earth masses and roughly 2.6 Earth radii, K2-18b may hold a deep layer of high-pressure ice inside, something more like Neptune's interior than Earth's. It might have a thin ocean above that ice. It might have a very hot ocean. It might not have a useful ocean at all. Notice how much uncertainty is packed into those maybes. That is why calling the planet habitable can mislead people. A planet can sit in the habitable zone and still be too hot, too pressurized, too chemically hostile, or too structurally strange for life. Distance from a star is only the first filter, not the final answer. Now another piece entered the argument. Researchers studying hydrogen-rich exoplanet atmospheres started asking whether DMS or related sulfur compounds might form through non-living chemistry after all. Lab work and models suggested the answer might be yes. That possibility weakened the simple claim that DMS would point cleanly to life. One important NASA-led reanalysis leaned directly on that concern. It argued that in the kind of atmosphere K2-18b may have, photochemistry could create sulfur-bearing molecules without biology. Photochemistry just means chemistry driven by light from the star. In other words, starlight itself may push the atmosphere into making strange compounds. That may sound like a technical side issue, but it changes the whole structure of the case. If a star can help make the same gas that life makes on Earth, then the gas alone loses power. You need context, multiple clues, and a much better understanding of the planet's environment. Without that, you are always one step away from fooling yourself. There is another reason for caution. Space chemistry is full of surprises. Scientists have found complex sulfur and carbon compounds in comets, in clouds between stars, and in places with no known biology. So a molecule that feels emotionally loaded to us may still be just chemistry playing a trick at a larger scale. Before the next reveal lands, lock in your next guess. Do you think extra data is about to make the DMS idea stronger? Or do you think the best clue in the whole story is about to lose ground? Leave your answer before we open the next layer. The next layer came in July 2025. A NASA-led study combined 4 new Webb transit observations with earlier data and analyzed them in a broader way. Instead of pushing one favored interpretation, the researchers tested several kinds of atmospheric models in parallel. That makes the result harder to dismiss because it is built to survive different assumptions. The analysis used Bayesian methods. That phrase sounds heavy, but the idea is not. Rather than asking only whether one neat explanation can fit the data, the researchers asked which conclusions keep appearing across many possible explanations. It is a way of checking what stays stable when you stop favoring your favorite answer. What stayed stable? Methane did. Carbon dioxide did. The evidence for a real atmosphere did. Those parts remain strong and important, which means K2-18b still stands out as one of the best studied habitable zone sub-Neptunes ever observed. What did not lock in was the biosignature claim. The new work reported only a tentative DMS signal at about 2.7 sigma. That is near the earlier level, but still below the stronger 5 sigma standard the field wants for a major detection. Instead of growing into certainty, the most dramatic clue stayed stuck in the maybe zone. That result changed the tone sharply. It did not kill the DMS idea. A tentative signal is not the same as zero. But it did show that repeated, better-tested analysis was not turning the molecule into a clear win for the life argument. If anything, the signal looked more fragile under pressure. This is a good place to separate 3 layers that often get mixed together. Layer 1 is what the telescope data directly support. Layer 2 is what atmospheric models infer from those data. Layer 3 is what those inferences might mean for life. The farther you move from layer 1, the more careful you have to become. Layer 1 is already impressive. Webb has given strong support for methane and carbon dioxide in K2-18b's atmosphere. The planet does appear to have a substantial atmosphere rather than being a bare rock. That alone is a real scientific step, because it tells us this distant world has active, measurable chemistry in its air. Layer 2 is more uncertain. A hydrogen-rich atmosphere fits the data well. A Hycean-style interpretation remains possible, but alternative planet structures are still on the table, including versions that are much less friendly to life. The atmosphere may sit over an ocean, or over hotter, deeper, harsher layers than the hopeful picture suggests. Layer 3 is the most uncertain of all. Life is not directly detected. No organism has been seen. No unmistakable biosignature pattern has been established. And the sulfur clue that created the biggest headlines remains both tentative and vulnerable to non-living explanations. This is why serious researchers keep using very careful wording. They say possible biosignature, they say candidate, they say hints. They do not say confirmed life, because the data do not earn that sentence. There is another hidden difficulty here, and it sits with the star itself. K2-18 is a red dwarf. Red dwarfs can be active stars, with spots and flares and shifting surface behavior. Those changes can affect the light we receive and make atmospheric interpretation harder, especially when the planetary signal is already tiny. Remember how the measurement works. Astronomers are reading minute changes in starlight from more than 100 light-years away while a planet passes in front of its star. The signal is delicate. Small errors in calibration, data cleanup, or model choice can push the answer in different directions. That is why strong claims must survive many separate attacks. This is not the first time the search for life has run into that wall. Venus once sparked huge excitement over phosphine, another gas sometimes discussed as a biosignature. That claim later faced hard criticism and competing explanations. Earlier still, possible signs of life in a Martian meteorite drew worldwide attention, then lost force under deeper scrutiny. Those older battles matter because they teach the same lesson. Nature does not reward eagerness. If a signal is weak, then hope will magnify it long before proof can support it. The only discoveries that last are the ones that keep standing after every simpler explanation has taken its shot. So where does that leave K2-18b right now? In a very narrow and very interesting place. It is still one of the best candidates for studying habitability beyond our solar system. At the same time, it is also one of the clearest warnings against treating one exciting molecule as the answer. What is still unresolved now is not a side note. It is the core of the matter. How deep is the atmosphere? Is there a true liquid ocean under it? And if so, what are the temperature and pressure there? Or are we dealing with a planet whose deeper layers are far too extreme for life, even if the upper air looks interesting? And if DMS or DMDS is present, what is making it? Life is one possibility, non-living chemistry is another. Without a better handle on the planet's full environment, the gas by itself cannot deliver the final verdict. It can only keep the argument alive. Now we are close enough to the end that the central claim has to be tested directly. Did the data confirm life on K2-18b? No. That answer is clear, firm, and supported by the way the strongest studies themselves are written. But the second question is where the story stays alive. Did the data confirm that K2-18b is just another uninteresting gas world with nothing special going on? No again. That answer is also too simple for the planet we are looking at. The chemistry remains unusual, the atmosphere remains important, and the possibility space remains open. Before the final verdict lands, make one last call. If you had to choose right now, would you bet on a real ocean world, a harsher mini-Neptune-style world, or some third type we do not yet understand well enough? Write your answer in the comments before we close this out. So here is the verdict, piece by piece. What the data actually confirm is that K2-18b has an atmosphere rich enough to study and that methane and carbon dioxide are present there. The data also support the idea that the atmosphere is hydrogen-rich. Those are not small points. The data do not confirm a surface ocean. They do not confirm a habitable surface temperature or pressure. They do not confirm DMS or DMDS at a level the whole field accepts as secure. And they absolutely do not confirm living organisms. That boundary has to stay sharp. At the same time, the story does not collapse into nothing. A hydrogen-rich habitable zone sub-Neptune with methane and carbon dioxide is already a major world to study. If some version of the Hycean picture is right, then K2-18b may represent a kind of planet that greatly widens where we might search for life. If the Hycean picture is wrong, it still teaches us what signals can mislead us. Either outcome matters. If K2-18b eventually turns out to host an ocean with chemistry favorable to life, then it may become one of the most important planets ever studied. If it turns out to be too hot, too deep, or too chemically strange, it still becomes one of the most valuable lessons in how not to fool ourselves. Science wins either way, as long as we stay honest. This honesty matters beyond one distant world. The search for life is not just about finding a thrilling answer. It is about setting a standard strong enough that the answer can be trusted when it finally comes. If we say life too early, we hurt public trust. If we ignore every hard clue because the first ones are messy, we risk missing the real thing later. K2-18b sits exactly on that knife edge. It shows how the search for life is changing from pure imagination into a hard measurement problem. Not an easy measurement problem, not a clean one, but a real one, where claims are built from light, tested by rivals, and reshaped when new data arrive. That should matter to anyone who cares about what comes next. The first confirmed sign of life beyond Earth will probably not appear as a perfect trumpet blast. It will more likely emerge from years of argument, repeated checks, and clues that have to survive every non-living explanation scientists can invent. K2-18b may be the training ground for that future moment. It also reminds us that life elsewhere might not look like the worlds we first expected. For a long time, people focused almost entirely on rocky, Earth-like planets. K2-18b pushed attention towards stranger worlds, worlds with hydrogen-rich air, deep oceans, or layered interiors that have no close twin here. That shift alone has changed the map of the search. Future tools will matter a lot here. Webb is powerful, but it was not built only to settle life claims. Later missions, including NASA's planned Habitable Worlds Observatory in the 2040s, may study promising planets with better tools for this exact problem. They could help turn hints into firm detections or cleanly rule them out. Until then, K2-18b remains suspended between promise and uncertainty. It is not the first proven living world. It is not a dead lead either. It is a planet that keeps forcing astronomers to sharpen their methods, question their assumptions, and separate what they hope from what the light truly says. So if someone tells you life has been found on K2-18b, the honest answer is no. If someone tells you the planet is no longer worth watching, the honest answer is also no. The real answer is harder and more interesting. This world is teaching us how proof of alien life might someday be built, and how easily weaker claims can rush ahead of the facts. If you want to stay ahead of the next shift in this story, subscribe and turn on notifications. Then tell me this in the comments. What would convince you that a world like K2-18b truly hosts life? And share this with someone who loves space but hates the watered-down headline version. Thanks for spending this time with me. I'm glad you stayed to the very end.